we have enough chairs? So there are two over there.
Yes, the two more. Do you need one?
I don't need one. Lecture 14. Parameterized complexity. Yes, can everyone hear me?
Absolutely.
No reaction, maybe my sound. Okay, thanks. Oh, but yeah, there is still a chair. You can sit closer. So I was ill, but now I'm more or less healthy again.
Bless you. Даже пуфик притащить,
if it's too cold, I will close it. Oh, and my lecture. So in the next 3 lectures, we will speak about parameterized algorithms. So there is a book in the references. It's a very interesting book. It's high level, so if you can solve exercises, you're very clever.
Sounds like a challenge.
Yeah.
High level, you mean it's a hard book or it's?
It's for master students, definitely.
Okay.
Yeah. It's you need so there are exercises.
I just thought that you mean like high level programming languages and low level.
Yeah. Okay, we're just chatting a bit because wow. I think someone will be sleeping soon. But it's nice though. Yeah. Yeah, there is another chair there. One out. Yes. Yeah, and here on here also somebody can sit. Yeah, my favorite place is here. Let me use the pen to speak about the structure of the lecture. Do I get all corners? So the topic of today is class FTP. So I will give some examples, and then I will speak what is kernel technique. It's a technique to make the input of your problem smaller. And so I did some project with company, and I applied some of these ideas, and they were extremely happy and giving me a lot of money.
Isn't it the same as a kernel trick in PCA analysis?
Principal component
principal
analysis.
component.
No, that's kernel of matrix. There are huge number of things that are called kernel.
Yeah,
Like
there is even a number of things that are called kernel tricks, like for instance support vector machines.
Yeah, just everything that's important is called kernel. And then we will speak about branching for vertex cover problem. So that's only 3. And then in the seminar we will do exercises about kernel technique. So making it. So there is a small theorem. So that problem has kernel if and only if it's in class FTP. So they're just this is the definition and a theorem. But you will see that the theorem is strange and useless. but interesting. Okay. So let's first go. I explained it already a few times. In the previous lecture we spoke about checking whether a problem is NP complete or NP hard. And so when it's NP hard, then we know that no polynomial time algorithm. So what should we do? So we should give a warning to our boss, like, okay, what you ask me is algorithm. So I will. So I cannot give you a provably correct algorithm that's always fast. So that's too much. Okay, but then there were some solutions. So let's say what it means. So there is no algorithm that works in polynomial time and give optimal answers for all instances. So 3 things. We said it before, polynomial time for all inputs and optimal answers. So usually we want a production problem, like produce a minimal vertex cover, produce an independent set that's as large as possible, and so on. Okay, so but from out of these 3 criteria, you can have 2 optimal things. Make 2 satisfied and drop 1.
For instance, we can consider an algorithm that doesn't work on all inputs, but maybe on some subset of inputs.
Yeah.
Or we can consider a greedy algorithm that doesn't always produce the optimal result. Works on all inputs.
Yeah. But for example, so approximate algorithm, like for vertex cover, we saw something in the lecture about approximation. So we can take an edge and put both endpoints in the vertex cover, remove it from the graph, and then repeat. It's kind of greedy algorithm, and it gives approximate answer and runs in polynomial time, and it works for all graphs. So just exact answer we drop in this case. Then other alternative is to look at special cases. So when we look at our input data for vertex cover, maybe we're lucky each time our graph is a 3, and then we can do something with dynamic programming, or just greedy algorithm, like put. Okay, I forgot. I should call it. Last time I also forgot and screwed up. Okay, yeah. So and then the third technique is to drop polynomial time and to do exhaustive search, and I think that's the most fun one, because you can then optimize the search, and then there are many nice techniques. So this book I just showed you, it's a really cool book if you have the time, and and it's kind of rewarding, but time-consuming job. Okay.
So now we are going to avoid the polynomial time.
Yeah. We will speak about exponential time algorithms, and our goal is to make the exponent as nice as possible. And so let us start with some simple example, and it is again vertex cover. So let me repeat after some months what is vertex cover. So we are given a graph. A vertex cover is a set of vertices that covers all the edges. For example, this graph, does it have a vertex cover of size 3?
Yes.
Yeah, so this one, and
any of the bottom.
Yeah, indeed, yeah. So do we have vertex cover of size 2?
Nope.
Can we decrease? I already asked you some months ago. No. And yeah, but it's kind of tricky to see why it is. So so there are 6 edges. So if we have vertex cover of size 2, we need to pick 2 times. So the total sum of degrees should be 6. And so the only way we can do it is pick this and this, because there's degree 3 and degree 3. But then this one is not covered. And if we pick any other node, it has degree 2. So it's kind of clever way. Of course, you can check all combinations and kind of. Okay. Yes. So in general, how can we solve vertex cover? We can solve it in n choose k time. So this is binomial coefficient. So n is a number of vertices in the graph, And the, oh, sorry, let me write the input, but you already know. So the vertex cover problem input is a graph, and the question. So do there exist k nodes? Graph and a number k. Do there exist k nodes that cover all edges? Okay, and we can solve it in brute force in time and choose k. So from discrete math, it is number of subset of size k from n different elements. So it's about, so good estimate of this number is, so E is this number 2.71 and so on to the power k. Okay, this is some advanced estimate, let's forget about it.
No, that's not. Why is this so? We know the direct formula, like n factorial divided by n minus k and k factorial.
But just I want to say that this is exponential. For example, if k is half of n, then there is even a better estimate. So then it will be around, so n choose n over 2 is 2 to the power n divided by square root n. So in the worst case, k is equal to this value. It's very slow algorithm. And so our plan is to do better than this. Okay, so now let us think about special cases where k is not too big. So we might be lucky, our k is a bit smaller. And so in parameterized complexity, okay, in the worst case, we have this situation. We try in parameterized complexity. We try to find a parameter, and when we believe this parameter is small, we have more or less okay algorithm. Probably still slow, but if a lot of noise here. But if our boss says, look, this problem is really important, I want to pay few CPU years, then we want to give exact answer. And so you can implement a clever program, or maybe CPU days or whatever.
CPU light years.
Yeah. So there is a programming exercises for this lecture and for the last the last lecture probably will be everything. I still need to invent the exercise, but so the grader I will switch on when I come home. I need to.
How do we submit them?
By email, and then the grader will download the email.
Wow.
Wow. And send you a reply back with your score.
What
and you can.
So we only have one.
No, you can submit many times, and it remembers your email address, and it will tell me what's the best score. I know that I should put up a server, but I'm not a programmer, so I just.
I mean, it's probably harder than a server to host it like this.
Well, I tried with server, but it was a mess. I don't know anything. But you know that for 15 years I have I worked like as a tutor, and I got so many stupid emails that I figured out to automatically reply with certain questions. And so I used this system.
Wow. Well, it's a non-trivial way, the most non-trivial I can think of. It sounds like you have 100 times more easier to set up a Yandex contest thing. But okay, it's great. Let's
okay, yeah, probably Yandex contest. I know that I had another exercise. And it was more complicated with several questions and several deadlines, and I had to use Smart LMS, and it was so annoying.
Oh, Smart LMS is absolutely dead story. Doesn't work at all. Most of the time, it just lays down calmly. And Yandex contest. I don't know in detail, but guys are doing it.
Yeah, you're right. Okay, maybe for the last lecture when I set up, I will use Yandex contest.
Can maybe consider it. Maybe it will be simpler.
But like I'm not so good in giving away control to to some computer. I want to program the grader myself. But it can do randomized, like when you submit, I generate a few random graphs. So to see that you're not trying to read the input, like, okay, I'm not gonna tell all the ways you can mess with the system.
Yes. Okay, so
yeah, distracted. Okay, what we want now is we have exponential searches, and there is nothing much we can do about the special case when we're at half of the nodes. Well, we can do a little bit, we will see, but what we will assume is that there is some parameter, and if it's not too big, then our search is hopefully good. So we will tailor our search according to some parameter, hence the field parameterized complexity. Okay, and so first algorithm is for vertex cover. So if k is small, so we can do something better. There is an algorithm that runs in power 2 to the k poly of n. So for vertex cover. And so this algorithm is branching algorithm. And how does it work? Well, what we do is we will pick an edge. It's a very famous algorithm. And what do we know when we look at an edge? What do we know about the two endpoints and the vertex cover? Well, just by definition, every edge needs to have an endpoint.
Yeah.
In the vertex.
One of the nodes
is in vertex
is
cover.
gonna be in the cover.
Okay.
Yeah.
And we can just pick one and then recursive.
Yeah. So we will recursive.
Oh,
Either
yeah.
we believe that this is in the vertex cover, or this is in the and then we can make our graph smaller and look for a smaller vertex cover. So you already see why this is. If everyone sees it, that's really cool.
I mean, you just branch out in k.
Yeah.
In k.
It's
I don't
2
know.
to the power of k
That's-
recursive branches, and every
Yeah.
branch runs in polynomial.
Okay,
time.
I will do
Yeah.
something boring
It's
because we will need so many recursion trees that I will draw one. So because then we have to do special things. So let's take a graph.
Am I right that it can be non-binary recurse search?
In general, yeah, but in this case it's binary, right?
Yeah. Okay.
Yeah. So let us have a graph
Как он,
here.
как он,
And then,
3 нельзя подключить к одному ребру. К одному ребру только 2 можно.
so let us think that this is our graph.
No,
It can be non-binary.
Yeah,
Okay,
So and then we
Yeah,
can
может-
say,
может
let us put
быть,
this node in the cover, and then remove all the edges that are already covered. And then we will have, okay, so this is, let us say that this is the graph which we start. So there are some slides, it's the same example. Okay, now I need to. So let us look at this edge, and then there are two cases. So in the first branch, we remove this node, and what is left is this thing. Yes, that's left. And in the other case, we add this node, and then what is left is this triangle. Am I right? No. So not much is left. Okay, and then we can take a new edge. It doesn't matter which one. Okay, so sorry, I didn't ask a question. So imagine that the input here is a graph, and we want to know if there is a vertex cover of size maybe 4. We need 4, and then here our instance is this graph and a vertex cover of size 3. So the answer to this question, if the answer to this question is yes, then to this question it will be yes. If here it's yes, then this will be yes. If they're both no, then answer is no. And so now we can. So.
No, it's obvious that it's yes on the left branch. The left one.
Yeah.
Yeah.
Okay. Okay, so where shall we branch? Maybe on this one, because with nodes of degree 2 it's kind of boring, or maybe even better on this one. Okay, you got it. So there is a case when this number, each level we go down, this number goes down by 1, and in the end we have a tree, and the number of nodes is 2 to the power k. Well, the number of leaves is 2 to the power k, the number of nodes is at most 2 to the power k plus 1, because it's binary tree, okay? Yeah, and then in every node we do a polynomial amount of computation. So what are the base cases? So when we go to k equal to 0, we check that we have dropped all edges. That's a base case. K gets 0, or there are no nodes left in the graph. It's also kind of base case. For example, no nodes and k is equal to 5, and then we say yes. And then it propagates up because every splitting is an OR. And to write this code is really short. So to get half of the score, you just have to write this. But you need sorry, it's a different algorithm. We will all see it. But it's equally difficult to program.
So it's a brute force, but just adequate.
Yeah, you need to. Okay, so you can also branch on the nodes. So you say either the node is in the vertex cover or all the neighbors are in the vertex cover. Clear? If this node is not in the vertex cover, then these edges need to be covered. So all the neighbors need to be covered. And this gives a better branching algorithm.
Better?
Better, yeah.
Always better.
And not always better. But we will speak how we can ensure that's always better.
Wow.
So we will add something. And then we will get a better power than 2 to the power k. But I'm going too fast and now. So our first goal is to say what is class FTP. So first I need to say what is a parameterized problem. And this is a problem where the input consists of 2 parts. One part is we call parameter, the other is just the rest of the input. And that's it. So before we spoke about languages. So a language is a subset of strings of some alphabet. That was old. Now a parameterized problem is a subset of pair where we have a natural number as parameter times sigma star. So this is parameterized problem.
Why natural? Why not real? We don't need any because we don't.
Well, we don't. Yeah, usually it's not necessary to have real parameters.
Okay.
But we will see that parameter is only used for some time bound, and then it's rounding doesn't matter much. Okay. Now, what is the class FTP? So FTP is class of problems that can be solved. So there is some input x, there is a parameter k, and then there is some question. And okay, here is a question, and the question can be answered. So a problem L is an FTP if there is an algorithm that runs in time, a function of k times a polynomial of the length of x. So let me write it. F is, so definition, language L is in the class FTP if there exists a constant C and algorithm that decides L in time f of k times length of x to the power c. Oh, sorry, and we also need the function f. So let's write f. F needs to be a computable function. Okay. That. So it's clear, right?
Can you repeat what is x?
So x is the input here.
And so c is in n, right?
Yeah, c is a constant.
C is a constant, then f is a computable function, right?
Yeah, so it can be exponential. And so in our problem before, for vertex cover, we had 2 to the power k times poly n, like.
So the language consists of some pairs, a natural number and a word.
Yeah.
And what is the natural number for?
For each problem is different. So in our case, k. Okay. So the natural parameter is when we have some production problem, is the size of the thing we produce. So for vertex cover, the parameter is this k.
And x is again.
So I mean, if we have a language, all the elements in this language have the same first element.
No, no. So k is a part of the input. K can be anything, but it's a special part of the input that we call the parameter.
Mm-hmm.
And the requirement on the runtime is that the parameter does not appear inside the power, or that at least there is a constant power.
A function f that decides L in f of k.
Yeah, so f is a function from natural numbers to natural numbers.
Yeah,
We give it a parameter, and for example 2 to the power k. So in this example we have f of k,
is
2 to the power k. But it might be 2 to the power k, and so on. So if we believe k is not too big, then we have a polynomial time. For constant k we have a polynomial, but it's a little bit stronger because the polynomial only depends on k in a linear. K doesn't appear in the power.
Why do we need f to be computable? Like f
It's
is just
for
a
some
boundary.
pathological reason. We won't need it, but there are some very unpleasant things.
So
The halting problem suddenly becomes weird things start to happen. Yeah, so we don't want undecidable, the halting problem to be fixed yeah, so actually most books skip this, and most books they write actually this to the power c, but we won't need this.
Why can't we just say f of k times poly of x?
So
So
f of
any
k,
times
and
any
that's
polynomial
any
of x.
polynomial, yeah.
Yes, that's the same.
Yeah, that's
Okay.
the same. Oh yeah, maybe if x is length 1 or so, okay. But then we can hard code the answer. Okay, yeah. I'm a bit lazy.
And f can be any function. It can be exponential.
Yeah,
Yeah.
it's allowed.
What means FTP again? Maybe.
Fixed parameter tractable. Fixed. Oh, sorry, FPT. Yeah, sorry. FPT, fixed parameter tractable. So there are some slides for this lecture.
So we are checking if whether the pair k and x.
Yeah, can be solved fast enough.
Okay.
So there is another class, you don't need to remember it, but maybe it's nice for comparison. There is a class XP, it's called slice-wise polynomial. They add X because there was no other letters left. And that means that it's solvable in time X to the power f of k. I don't know how, maybe I should add big O or something. So the same definition, just a larger, this is called slice-wise polynomial. And so our algorithm that tries all subsets here,
Yes.
that was an algorithm that proves slice-wise polynomial. because the runtime was bounded by x to the power k. This
and f is
and
just
k is bounded by this term. So independent set problem. So graph and a number k. Do you find an independent set of size k that has no connections in the graph? It's slice-wise polynomial, and it's believed you can do no better. In the last lecture, I will explain how this is proven. Okay, let me write that. I had some example. I will just state some problems. So click with max degree. What did I write? No, that's not. Sorry, yeah. Click with the natural problem. With the natural. Sorry, there is also a definition for two parameters in FTP. So if you have two parameters, k and l, for example, then there are two ways to define it. So you allow f to depend on two parameters, or you have f with one parameter and you apply it to the sum of the parameter. And so an example is click with maximum degree and the size of the click. No, just with the maximum degree. It's a good example. So this is also FTP. Vertex cover we already said.
Max degree is the parameter.
Maximum degree of a node. So here it's 3 because all nodes.
It's the parameter of.
The parameter is maximal degree. Then subset sum problem, like given a bunch of numbers, can we select a subset of these numbers that reaches exactly target value? And then if the parameter is its target value, then it's also FPT. And then the independent set problem, and there we have both the max degree and the size of the independent set. So there are 4 examples of problems that are FPT.
There is a typo in the left.
Yeah, I also. Yeah.
File transfer protocol.
Yeah. We were talking too long about servers. Okay. So problems that are in. So there are some problems. So it's problems in NP that are also in FPT. They're kind of easy. So you don't need to be desperate. But if they're outside FPT, then it's your life becomes much harder. For example, click an independent set problem. So then you need to try to find more parameters that are likely to be small in the problem. Okay, so yeah, click with click as click size, a natural parameter, and it's not an FPT under some hypothesis called exponential time hypothesis. It says that SAT cannot be solved in sub-exponential time. I mean, roughly said. It's slightly more subtle, but it's a very important hypothesis. So you often see it in papers more than, it's just 10 years, 14 years old or something. It's a recent thing. And then the K colorability problem. So given a graph and a number K, can we assign one of K colors to all the nodes so that every edge connects nodes of 2 different colors? So this problem is not FPT when K is a parameter.
It is NP complete, right? K color.
Yeah, so tree colorability is NP complete. So assuming P doesn't equal to NP, we know that we cannot have this runtime, because if we set K equal to 3, it would be a polynomial. So assuming P is not equal to NP, not equal to N, let me write it. P not equal to NP implies K colorability is not in FPT. Not in FPT. And it's also not slice-wise polynomial for the same reason. So here is the bound for slice-wise polynomial. If we set K equal to 3, we again have a polynomial. So in practice we assume P not equal to NP, unless you really like SAT solvers or MILP solver or whatever. Okay. Yes. Okay, let's do one more example. Okay, some simple observations. So P is a subset of FPT. So can you understand this? So P is a subset of FPT. So there is a little formal detail. We don't have a parameter, but let's just put whatever in this parameter, like 1, constant 1, or the x itself, or whatever we choose. We always have that this is true. So why is it?
Because P is polynomial, we can just take F as identity, K is 1, x of C,
yeah,
go of x of C.
Easy. If P is equal to NP, then NP, all the problems, and so this is direct consequence. So whenever we want to prove a problem doesn't have a solution with this runtime, we will need to assume P not equal to NP. So this assumption, exponential time hypothesis, that SAT cannot be solved in sub-exponential time, it's a stronger assumption. If P equals NP, we can solve SAT in polynomial time. So this is, we needed to say that clique is not FPT. So that we need stronger theoretical assumption. Okay.
Exponential time hypothesis is weaker than saying that P equals NP, right?
So P not equal, so
NP it's a stronger assumption than exponential.
So yeah, exponential time hypothesis is stronger assumption. So for example, maybe SAT can be solved in time square root of n, where n is the number of variables of the SAT instance. Then exponential time hypothesis is wrong, but it's still possible that P not equal to NP.
Okay.
So it requires every function
exponential time says what again? That it exponential on times of
so that there exists a C such that solving SAT requires okay, I should carefully study this because it's kind of subtle exponential time hypothesis. I mean, there are good reasons, so and I didn't look it up, so so let's do another example of a problem. So now one with 2 parameters, 2 or 3. I already said. So let us look clique with the maximum degree as parameter and the size of the clique. So input graph. Then okay, another thing I say that there are actually 2 variants where the parameters are part of the input and not part of the input. But we will always use part of the input just for simplicity. So max degree. Degree P, and then a number K, and the question graph has clique of size at most K. Okay, that's our problem, and now the task is to prove that using both so we know that without this parameter it's not an FPT, but with this parameter we can prove it's an FPT.
Max degree of a node?
Yeah, so every node has degree at most some parameter.
I can prove that it is
max degree D K. What K means?
K is another. So K.
Okay.
This is the size of the clique.
Okay.
And then the max degree. And so the question is, how can we prove it?
That it is a FPT. an algorithm.
By providing some algorithm.
Exactly. The question is which algorithm. So what is a clique?
Clique is a connected component.
No. Connected component. Well, okay. Connected component in a graph is you pick a node, and all the nodes that are reachable from this node, they're called connected component. But a clique, almost right. So just a set of node, and every pair of node is connected.
Yes.
It's a strongly, no, not strongly.
That's for directed graphs, that you can go from every
Yeah,
node in the
yeah.
clique to the other and vice
Yeah,
versa.
I see.
Yeah,
Every pair of nodes in the clique. are
yeah,
connected.
is connected by an edge.
So it's like a full
Yeah.
subgraph.
So here,
That's what I was trying to
so
say.
this graph has a clique of size 3
Three needs the
yeah,
triangle.
because there is triangle, but it doesn't have a clique of size 4 because we need both diagonals, or
No, we don't need both diagonals. We just need one of them, and there will be a clique.
no,
of size
this is
4.
not a clique. So this is not a clique.
No, on the top.
Yeah.
Triangle and this bottom.
No, on the top.
Да, сверху снизу.
Yeah.
Okay.
Yeah, we need
Yes. We
6 edges. Yeah.
But
Yes,
I have a question.
Now
Yeah,
there
yeah.
is-
Now
yeah.
that's
Yeah. Okay, so now we understand what's a clique. It's very important for this exercise. Yeah.
The question is, so the question graph has clique of size at most k, but if we have a clique a larger size, we can just take any subgraph of this clique and it will be a clique also. So the question is just the graph has a clique of any size, no?
Sorry, at least k. Yeah, good point. yeah. This is very important. Okay, and then there are values for k for which it's easy to answer. For example, what if k is larger than d?
No. The answer
Then
is no.
yeah.
Yeah,
Of
yeah.
course.
Well,
As we need at least d.
so if the,
At
k,
least
K minus
edges
1
to-
edges.
yeah.
We need some nodes with k minus 1
exactly
edges.
K, yeah.
If we have d plus 2, we can directly say no.
3. That's better.
Ah, yeah,
Because in
yeah.
triangle we have
Yeah.
degrees 2, so then there is a clique of size. But when it's
Yeah.
larger, then so it's already a first hint. So we can assume k is at most d plus 1.
Mhm.
And so I will tell you something. The algorithm runs in time 2 to the power d poly n number of nodes in the graph.
Maybe something similar to branching, like take a node with that max degree.
Find all the neighbor nodes with max degree,
Yeah.
and you check if they form a clique or not recursively. Kind of like that.
Almost.
Uh,
Maybe
Okay,
somebody
but-
from home or from Zoom.
Okay. Do we always need to pick a node with maximum given degree? With maximum.
Yeah.
Degree?
So
Kind of.
If we don't,
Seems like no. We need to pick nodes with with degree k minus 1 at least or more. With k minus 1 or more. So yeah, and what's next? Okay, let's say we choose a degree, we pick a node, then we look at all the neighbors, and if they're all with the same degree,
we need to delete it somehow. Like, I think.
yeah, what you say is recursion is good, but it's easier the answer. You can answer more easy. If you want to have this time, if you implement, maybe it's a good idea to to speed up, but just say the easiest algorithm. Okay, I will tell you,
Okay.
because you basically can. So we just go over each node, and for each node, we check whether this node and some of its neighbors forms a clique.
Yeah, it's
And so what we have to do is just check all k-element subsets of the at most d neighbors.
of k elements.
Yeah. So subsets on d elements is at most 2 to the power d.
Mhm.
So we check all subsets of
Okay.
neighbors.
So, I mean, we just take a node and check if its neighbors form a clique.
Yeah.
If they do, then the answer is yes. If
Yeah.
they don't, for all of the nodes, which
Yeah.
is n,
Yeah.
they don't.
Yeah. Then the answer is no. Exactly.
Isn't it exactly n by 2 to the power of d?
So it is.
We need to.
If you want better bounds, it is we have d neighbors, and we have to choose k of them.
Yeah.
K minus 1 of them.
Mhm.
So that's a better bound.
Mhm.
And,
Or we could do like you say with recursion, and maybe we get. But no, because it's FPT, but now with length of x being d, so it will not so much gain. But when you implement it, maybe it's like in the end of your implementation, you can try to speed up like this.
So it means that then the less d, then it's better for us, yeah?
Yeah.
Uh,
Okay. So since this exercise go well, let's do the same for independent set.
Let's just take the inverse of the graph and do the same. If the graph has an independent set of size k, that means that the inverse of the graph has a clique of size k.
Oh yeah, that was fast. Okay, but I will continue to speak about. Okay, so we finished with our first point. Let's now go to kernel. And so I will make a different algorithm to prove that's an FPT.
could you please remind us what is
Independent set. Yeah. So here's the graph again. It's a so it's a set of nodes for which any pair on the set is disconnected.
Okay, see, thanks.
Yeah. So, for example, this graph has independent set of size 2. So this and this one is in because these two nodes are disconnected. But it doesn't have an independent set of size 3 because whatever pair we choose and whatever third node, well, we have only 5 nodes and there is a cycle. So if we choose 3 nodes, there must be. So there is a cycle. Even if we ignore this one, there is no independent set of size 3. Okay. Yes. So what I'm so now I will explain what is kernel, and I will do it with an example. But maybe I should use the vertex cover as example. Yeah, vertex cover. Oh, cluster graph. Yeah, let's do another example about FPT. I think it's a good idea to have for this definition. So the problem we will consider now, input is again a graph. Parameter will be some number k. And okay, first the definition. What is a cluster graph? It's a disjoint union of cliques. So example of a cluster graph is something like this. So that's kind of weird graph. Weird definition you might think, but actually it's very useful, a cluster graph. For example, in genetics or proteins, So people want to know whether genes or a bunch of genes belong to partition in animals, and then they check, they connect two genes if they're quite similar, and then each cluster are different animals from the same species, for example. But normally when they try to do this, there are some faults and there are some defects. So maybe it's something like this, and this connection might be a defect. And so here is the problem. Given a graph, can you delete at most k nodes to get a cluster graph?
We can use spectral clustering, an algorithm that utilizes Laplacian algebra.
Yeah, and so this problem is NP hard.
Yes.
So that means these answers are not always always correct for this discrete version of the problem. So the question, can you delete k nodes to get a cluster graph? So cluster graph, disjoint union of cliques. And so here in this example, we could delete this node or this node. So that there, for these animals, maybe something went wrong in reading the genes. Like in the device, DNA for two species get mixed up or something. Okay. Yes. And so this problem is NP hard, but fortunately it's an FPT. So if we want exact answers, we can write an efficient algorithm. And there is an algorithm that runs in time 3 to the power k poly n. So how does it work? Well, let us check what are the cluster graphs on 3 nodes. Let us look to all the graphs on 3 nodes. So I will make. So there are 4 non-equivalent graphs.
And the completing.
So 0 edges, 1, 2, or 3 edges. So which ones are cluster graphs?
The only one.
Yeah.
No.
First, second, and the last.
Yeah, indeed. But this is not
second,
cluster graph.
Because it is not fully connected, so it's not a clique. And it's not also the edges join.
Yeah. Okay. So now there is a little lemma. A graph is a cluster graph if and only if for every 3 nodes, every triple of nodes, we have one of these cases. So the induced subgraph is one of these 2 cases.
So you can just select all triplets and check if they belong to it.
That's indeed the algorithm. Yeah.
Can you repeat?
So graph is cluster graph if and only if every triple of nodes either belongs to these 3. Or in other words, for every triple of nodes, this does not appear. So let's prove it. Why it is true. Should I write the theorem? Or you can make, okay, let's write it. So G is cluster graph if and only if for all U, V, W the induced subgraph is not U, V, W. So we just look at these 3 nodes, and then we know that if U is connected to V, V is connected to W, then it's not a subgraph. But if for every triple of nodes we do not see this, then it's a cluster graph. So for example, this is not a cluster graph. What can we use for U, V, and W?
The circled ones and
U, V, and W.
Mhm.
So because we have these 2 and these 2.
Okay.
And so how do we prove this? Okay, so let us say clear again what is cluster graph. Every connected component is a clique. So that means that if we pick any two nodes that are connected by an edge, then these by a path, then they are connected by an edge. So again, if every two nodes that are connected by a path, they are connected by an edge.
So they belong to one clique.
Yeah. So that's a property we need. And what we have here,
and
we
have
pick
a
three nodes,
contradiction, yes.
Yeah.
and they are not connected by an edge.
Yes.
But then we have an edge. So here we pick two nodes, W. But then it can happen that so this is not a cluster graph because we find two nodes. They're not connected by an edge, but they are connected by a path. So now we need to come up with three nodes. Okay, so to prove this equivalent. So there is one easy direction, one difficult direction. So easy direction is that if it's a cluster graph, we will not see this thing.
Yes.
This is obvious. Now, if we do not see this thing, then it's not a cluster graph.
If we
So let's go to the reverse. If we do not see this thing, then it's not a cluster graph. So if we do not see this, it is a cluster graph.
Yeah.
So the contrapositive. If it's not a cluster graph, we do see this thing. That's what we have to prove. Okay. So what we said.
If it's not a cluster graph, we do see this thing. It's
Yeah, not cluster graph. Therefore, we see two nodes with two disconnected nodes with common neighbor.
Okay, so
And now, not cluster graph, we see this. That's what we have to prove. Okay, so not cluster graph, we have two nodes that are connected by a path but disconnected. So so how do we choose U, V, and W?
So we choose big the UV on the sides and any in between.
Yeah. So.
Yes, and now let's say this.
But we might be unlucky. We might have this. So we pick any node on the path, and if we're unlucky, then we are lucky. But we might be unlucky, and there is no edge here.
Yeah.
But then we move W to here, and U and W become closer, so we can repeat. So let me say it again. So we have a path from U to W.
Okay.
And so we pick any node V on this path. In the middle, or if you want, next to W. And so there are two cases. Either V is connected to U, and then we are finished. But V might be not connected to U. And then we move W closer. Here. And then we again search for
choose
V,
any,
and we keep repeating until W will never be next to U, but it will be a distance.
Because if we have V in the middle.
So we don't move when they're connected. So it will in the worst case it will go to distance 2. Okay, it's clear. Yes.
Good.
And now you already said what is the algorithm.
Yeah, we need to select all the tripods.
Yeah. So we will. So we will search for the forbidden triple.
Yeah.
If we find none, if we tried all triples and all of them are okay, all of them are of this type, then we conclude we have cluster graph. And otherwise we find such a triple and then we try to remove each of these nodes. So we drop U and then we repeat the process. So then we do recursion. So and we decrease k by 1 because we can now at most k minus 1 nodes. And so we will have a recursion tree, but now with 3 legs.
And what's the asymptotic complexity?
Oh,
It's
this is very easy.
It's
So
definitely 3 to the power of
We can at most delete
to the
key
power
nodes.
of k, 3 to the power of k,
Yeah.
and we find we check all the triplets by add
time poly n.
y time.
So we have 3 to the power k poly n, where n is the input, the number
we
of
need to
nodes or
select
whatever.
3 out of at most n,
Yeah.
right? And it's
3 choose n, which is
It's
n to the power 3.
is it
So you make
Oh,
3
it's,
loops over all the nodes.
And then in
это, блин, даже факториал, в смысле, как поле это?
Okay, so there was a little break.
Типа там n факториал разделить на n минус 3 и на 3 факториал. Ну, на минус 3 факториал на 3 факториал.
Все
Да,
тройки вообще давай с другой стороны. Все тройки добавим в третий.
Это с повторением.
Да. Ну, выбираешь повторение.
Okay, so half an hour.
Yeah.
then.
3 вен. Сейчас напишем.
So,
Все
is
тройки.
it a break now?
Well, it's
Yeah,
7:14. So, but I have we only finished this one. But this one is quite short, and so
okay.
yeah.
Не, ну да, то, что прощается.
You just
Повторение
said
там
that
намного
it's
меньше.
a little
Там
break,
просто
and
n
I
минус
just
1,
told
n
that
Yeah,
минус
I
I
2.
can go
Yeah.
on by.
No, sorry, half an hour, and then
Okay,
we'll
okay.
have break. Yeah.
Окей.
Okay, maybe I can open the.
Ну да, ну это точно n в третьем. Ну так что мы...
Ну да.
Все, чеф. Там типа, ну я же говорю, это n на n минус 1 на n минус 2 поделить на 6. Полиномер, действительно полиномер. Sorry,
It's a break now?
No.
Oh,
We will do a kernel and the funny definition and funny theorem. But first example for kernel with vertex cover problem. And again, the parameter is size of the vertex cover. Yeah, so it's 7:10 now. So the lecture is an hour and 20 minutes. So
Yeah.
but we started a bit later, and I will finish kernel for sure. And so graph parameter k has a vertex cover of size at most k. And now we have a very a topic that leads to a lot of money. I mean, just on my work account, so for hiring people. So, well, if I want, I can transfer to my account, but just I bought some bitcoins. I don't see the point. 1 year ago, so I put all my savings in bitcoins, and then it was, yeah. So I don't know why I'm working anymore. So because it might find ×3 or something since 1 year ago. Yeah. Okay, so I'm distracted again.
Distracted by money. As well.
Yeah.
Money is still.
Okay. Oh no, but I shouldn't say this on YouTube. Try to find accounts. Okay, I just cut it out. Yeah.
What's the
vertex
parameter
cover?
again?
Yeah. So what is our plan now? We want to solve vertex cover problem, and so we had some runtime, 2 to the power k times n squared, for example, or maybe a RAM model with careful implication. It's something like this. And so now we want to reduce this factor n. Okay, it's not so impressive maybe, but there is some general technique, and soon it will become impressive. So the techniques will start to combine, and suddenly it will be impressive, hopefully near the end of the lecture. Okay, and so for vertex cover, there are certain things we can do to make our problem easier. First example, so it's supposed to be a scissor. Let's drop all nodes of degree 0. They have no edges. We have not to do anything about them.
Can you repeat what's the parameter? The same as before?
Yeah.
It's
Parent
the
k,
size of
yeah,
the
vertex cover of size at most k.
Ah, okay.
At most.
Yeah.
At least
That's
maybe.
it. No, now it's at most. So the the clique and independent set should be large, the vertex cover should be small.
No, but we
So
we have a vertex cover of size 1 and we always
no. Of size
Ah,
n
no,
we
of
always
vertex
have.
cover,
We
no,
could
not
take
independent set.
Yeah. But
Sorry.
complement of vertex cover is independent set. So independent set we want to be large and the clique should be large, vertex cover should be small. Okay. So first rule, drop nodes of degree 0. Second rule, okay, sorry, now it will be totally not impressive, but okay. So second rule, oh no, what was the second rule? If you have a node of degree k plus 1, what do we know about it?
K plus 1, k is the size of the vertex cover. It must be in vertex cover?
It must be in the vertex. If we don't pick it,
Yes.
then we need to cover all the neighbors, because the edges to these neighbors need to be
And
covered.
it is more than k.
And it's more than k. So next, reduction rule, remove node of degree k plus 1 or more, plus 1, and k goes to k minus 1, and then recur. So decrease k by 1. So we have a new problem. So we remove the node, we get a new graph, and we have a new value for k equal to k minus 1 of the old variable. And then these are equivalent, these problems. So in the new, so what we do each time, we get the graph and k, and then we map it to a new graph g prime and k prime. And the answer on these two graphs is the same. So if we drop a node of degree 0 and we keep the same k, answers remain the same. So we are just rewriting our input and each time easier. Okay, and now next rule. If graph has more nodes than, if a number of nodes more than k times k plus 1, say no. We can right away. So we apply these rules until it's impossible, and then we apply the third rule. So each time we see a rules like this, we do the first rule until we can. Then we apply the second rule. Then we again start from the top until we can, and so on. And so when we have applied this until we can't, and then we see there are k times more than, strictly more than k times k plus 1 nodes left, then we just say there is no vertex cover.
Because k times k plus 1 is the number of edges on fully connected, twice the number of edges on the fully connected graph of size k.
Is twice the number of edges
On the fully connected graph of size k, right?
Okay.
Ah, no, it's
So the question is, why don't we make a mistake here? Why it's still equivalent? So when I say no, I just output empty graph with, or just graph with two nodes by an edge and k equal to 0, and then it's no. Yeah. So why is this right? Okay. So let us think that the answer is yes. What do we know about the size of the graph after we apply these rules? So let us think that vertex cover exists. So there are k nodes and they're vertex cover. K nodes, and they cover all the edges. We know that they have degree at most k. And same for this. So all of them go to k nodes. Okay, how can we have more nodes in the graph? So here we go to at most k nodes. So what's the maximum number of nodes we can have so that none of these rules can be applied? So here we know that the nodes in the vertex cover. So we assume vertex cover exists. And then we check what's the maximal number of nodes in the graph.
And it's k times k.
Yeah, if
So
all
we
of the
know that
nodes
the
are-
degree of each node is at most k.
Plus 1. Okay.
There are
Yeah.
no isolated nodes. And so this node can be connected to at most k nodes, and the same for here. So if the answer is yes, so if yes, then number of nodes at most k plus k squared.
Which is
K plus k squared.
Which is k plus 1 times k.
And so this rule is correct. And this is great. So why is it great? We may start with arbitrarily large graph, and if k is small, we end up with the graph of order k squared.
If it's if the order
Yeah.
is higher, then we
Yeah.
definitely just put no in. So
And so we can improve. It doesn't matter which c we use here. So we go from 2 to the power k to 2 to the power k to the power k squared to the power c. And so we can have 2 to the power c. It doesn't look impressive to you at the moment. So if n is 5 million and k is 100, then
it
it's
makes sense.
yeah. It
But yeah,
helps.
but still, if k is 100, then it's 2 to the power of k, and it's still computationally impossible in practice.
Yeah, but we're not finished yet. So we will get to k. Maybe not in this lecture, but okay. So 2k, 2 times k instead of k squared we can get.
No, I mean 2 to the power of k. Still,
Yeah.
Still is
But we will have 2k. So we replace n by 2k.
That's interesting.
Yeah, so from 10 million to 100, for example. Yes. Okay, now let's explain what is kernel. Okay, so people are still looking to the board.
Yeah, I have a question. So in the second step, we just select some node that has a degree larger than k plus 1. But what if we don't have such node?
Then we are finished with this rule, and we can go to this rule. So each time we start on the top, and when we can do something, we start again from the top. And if this rule can no longer be applied, it means that we can go to the next rule.
And if
No, we need to check the first rule, no?
Yeah, after we apply this,
Yeah, we need to
we
check the
check
first.
on this, and
and
then after we check this rule, it cannot be applied, we go here. So that we will always make like lists of reduction rules, and we go each time through them. I mean, it's not always necessary, like when you're programming, you can be more lazy, but you need to know the proof. You can
And why
choose
don't we
the
go?
order.
Why don't we go to the top to the first rule again after?
Well, in here, the order of these two is not so important. We
Yeah,
can
but-
always change them, but this we can only do if this can no longer be applied.
None of this can be applied.
Yeah.
So yeah.
So
So basically, we apply the first rule, then we, as much as we can, then we apply the second rule as much as we can, then we go back to the first rule, and if we cannot apply the first rule only, then we go to the third.
that works also. Yeah.
Okay. Otherwise, we just repeat the process.
Okay, and so now we can say formally what is
a kernel?
What is kernel? Need some space. Let's write it here. Okay, no vertex cover. So K will map inputs of our problem to other inputs. So n times sigma star to n times sigma star, and K needs to be polynomial. If K is polytime computable. And so what we want is that the parameter doesn't explode completely. Okay, there's some formal definition. We require the parameter to be bounded by computable function. Again, this weird technical thing. So n exists computable function. It's almost automatically satisfied, especially in our case where we have part of the input. Okay, computable function S from n to n, such that size k of x smaller than s of k. F. No. Sorry, F is kernel if. So k. I didn't start my definition right. Okay, let's delete. Okay. Sorry, for is kernel if. Sorry, for there exists polytime computable if it is. So first condition, it should be polynomial time computable. Second condition, there exists computable function f such that this is true. And 3, it should be equivalent. So kx in L if and only if k of kx in L. So these are 3 requirements. So that's definition. So sorry, it was boring when I was writing.
What's S of k?
So it's just some function, computable function from natural numbers to natural numbers.
Okay.
And so we want the size after the reduction to be only a function from k. So remember, in our vertex cover example, we had k squared for the size of the function because of this third rule. If it's larger than k times k plus 1, we directly give the answer. So directly give the answer just means that we pick in as the most simple instance where the answer is yes or no. So if the answer is yes, we put out an empty graph with k equals 0. Then the answer is yes. If the answer is no, empty graph, graph with one edge and k equals 0. Then the answer is no. So we, after mapping to the new instance, so we have 3 conditions. Reductions should run in time, polynomial time, in the size of the input. So that means in polynomial time, and time polynomial in, let me write it, is computable in time poly length of x. Okay, and in the books actually they write length of x plus k, but I will be lazy, just write time of poly time of x.
Because it doesn't matter, it's constant. The parameter. If we go off
well,
length of
I
x.
mean k can be a number in binary, and then for example for subset sum, yeah, actually maybe I should not do this, but I will be consistent with the slides.
Okay.
So there are some cases, okay, now I need to be careful with exercises, but let's just use the simple definition.
Okay. There exists a computable function with the size of...
Yeah, so the size of the new instance.
What is the size of the new instance?
Ah, yeah, okay.
It is...
So the size of the x part of the new instance to be consistent with here. So it means let us say that size of xk is equal to the size of x. So here we look to the input part. Okay, I'm a bad person. I should stick with the definitions of the book, so I might. Okay, but for now, let's fix it like this. It's just 3 lectures, we will not go too deep.
And kx is in L, k is in which means that k doesn't screw up our problem, right?
Yeah, so we make the problem very small. It only depends, okay, is typically small, like 100 or something in the vertex cover problem.
I mean,
and even if x is 10 million, after the reduction we end up with some function of 100.
So k acts on inputs, right? So we have a decider for our problem, let's say, and we have the inputs to it.
Yeah, the decider gets both k and x.
Yeah, so the
parameter and x. Okay, so this is definition of kernel. And now there is a nice theorem. So problem has a kernel if and only if it is in the class FPT.
Interesting.
So now the proof. So and the proof is very short. So so assume so algorithm decides L. So let alg be an algorithm. Let alg decide L in time f of k times length of x to the power c. Let alg be c. So f, alg, and c, the triple from the definition of FPT. Okay, and now kernel k of x. This run decider. So run this alg for time length of x to the power c plus 1. If halt, output answer. So if this algorithm finishes in this time, then we can tell the answer, just fixed instances for which is yes or no. And then otherwise, output kx. So that's the algorithm. So 2 rules. Run the decider. So this is the running time, but we run it for this time. If we get an answer, then we output the answer. Otherwise, we output the input itself. That's our kernel. And so now we have to check the 3 conditions of definition of kernel. Oh, by the way, I forgot to tell there is easy direction in the theorem. So what's the easy direction?
If L has a kernel, then it's an FTP.
Yeah, and why is it?
Because
applying the kernel and then
deciding.
Yeah, so what is the runtime? F of the parameter, which is bounded by O.
So
F and S.
Yeah, the parameter should also be bounded by S. I forgot to tell you in the size definition. and then we have x, which is also bounded by k to the power c. And so this is a function that depends only on k.
The parameters should be bound by what?
Okay, so when I said that smaller kx is smaller than, so what is this? It should be equal to the max of k and length of x. Sorry for this. Yeah.
So
okay, now we see that. Okay, I cannot. Yeah. Okay, this is very messy. Okay, I will write notes to fix this and send it to you. Yeah, only about kernels I will write notes.
Thanks.
Yeah, and I will update the slides if I can find the LaTeX. Okay, but so now let's go to the real definition. K plus length of x. It's the real definition. Now I'm not trying to be lazy and then getting into trouble. So it's the real definition of length of an instance. So we require that this is bounded by s of k.
Since they are both positive,
Yeah.
Each one is bounded by s of k, and so the problem is in FPT.
Yeah. Okay, and so what is the runtime? So we have polynomial, so I claim that if it has kernel, it's an FPT. Why? We run the reduction,
and then
which requires polynomial time, so we don't need to worry about this time. And then we run the decider. And what is the time of the decider? It's f of the parameter times the length to the power c. But here the length of the reduced instance. Okay, the length of the reduced instance is at most s of k. Yeah?
And the length of the parameter?
And the parameter is now also at most s of k.
The value of the parameter is at most s of k.
And so here we have something only depending on k. Here also something depending only on k. So we get something better for the bound on the runtime. So when we combine both procedures, the decider of L has kernel. Oh. Okay, I see. And strange. And L is decidable. Okay, now it works. Then L is an FPT.
Where we get that f of the parameter and the power?
Yeah. I messed up. Okay, so decidable. So let h be the time for which is decidable. So now we will apply. So h get a length and tells the time. So h is a function that, given the size of the instance, tells the maximal time to decide it. Okay, I will write it more nicely. But then I need some space. Okay, so L is decidable in time, so h, so the question kx in L, so this question is decidable in time, h of size kx. And h is some computable function. Okay, I understand now why we need computable functions. Okay, so and now we want to prove its FPT. And we also know that L has kernel. So what we do, we apply the kernel, and the output of kernel goes to the decider that runs in time h. But after applying the kernel, the length of kx only depends on the parameter k, because of second condition. So we can assume h is monotone, so decidable on all inputs of. So you understand, you can assume h is monotone, right? Because unfortunately we have inequality here. That's why we want h to be monotone. Polynomial time reduction to something smaller than this, and now this decision procedure, this computable function, the runtime only depends on parameter value. Okay, so what is the runtime of the combined procedure? It is kx to the power of 1 for the reduction. First we need to make it smaller, and then h of s of k. And here I use that h is monotone because in 2 we have inequality. So this is the runtime, and this is really cool. So we have a we went from polynomial, from function of k, from function of k times polynomial in x, we went to function of k plus polynomial in x. That's a really cool thing about kernels. Like the painful function gets separated as an additive constant. Yeah, so this is this direction. And unless I said, it's not at all easy, and my statement was even wrong, and I messed up. So, okay, for punishment, I will write it in the next days. By Friday, I will write it. Okay. Okay.
So now it will be the hard thing, the hard bottom.
Yeah, but now I think that this was actually the hard part. The other part, algorithm is easy. So if there are no questions anymore, I will delete this in the bottom. Okay, so now we assume L is FPT and we construct a kernel, and I already explained what's the algorithm. So we run the algorithm that decides it in FPT formula time. If we get an answer, we output it. If we don't get an answer, we output the instance itself. Now we have to check 1, 2, 3. So first, does it run in polynomial time? Yeah, that's clear because of this condition.
X to the power of c plus
1. Okay, 1 is good. 2 is the length. Let us start with 3. Is it equivalent?
Yes.
Yeah, clear in both cases. Here we are very safe, and here we are safe also. So now 2 remains. So the question is the size bounded by a function only of k? So here we are good for 2. So here we just output the answer, so the size is constant. We just pick the smallest where it's yes, the smallest where it's. So here the size is a constant. Now here, this case, we have to check. It's our last task. Okay, so here we know that the runtime was larger than this thing. So what do we know? Here is our runtime. So we know f of k times length of x to the power c was larger than x to the power c plus 1. Look, we are done. We've proven x is small.
We have proven that f of k is larger than
yeah.
x.
So we cancel x to the power c here, and what remains, f of k is larger than size of x.
So but
When did we prove that the first statement that f of k multiplied by...
That was in the other direction.
Oh,
so now
okay.
we have something cool. When our problem is in FPT, we have a kernel, and then we went from times to plus. But it's kind of logical with these huge functions. If you multiply them, it's just like increase the power a little bit in one, in the largest side, and then yeah, it's not so surprising actually. So this is completely empty proof, but it tells us something interesting, that this cleanup will always be successful, even for stupid reasons.
Why do we care that f of k is greater than size of x?
Because we need the second condition.
Yeah.
In this second condition, on the second branch, we output k and x, and we need to check that the size of k and x is actually bounded by computable function of k. We know that the size of k and x is k plus size of x. The size of x is lower than f of k, which is a computable function, and obviously k plus size of x is lower than f of k plus k, which is a computable function as well. So we can just set
So yeah, that function is the s function, kinda.
No, s function is f of k plus k, right?
Yeah,
Yeah, because we need to
yeah.
Okay.
from the size.
Cool. So we are finished for today. So this I will explain. It's not so much. I will start next lecture, and then we will have better kernel with size 2k next lecture. But it's not needed to program for now, because it's with linear programming, and it crashes on. So I don't know. So linear programming, it's unstable around 200 parameters, and same number of inequalities. So when you program, you don't need to. So only things for today. Okay, the programming task. I do need to explain a little thing, but let's have a break now,
Okay.
and then I will explain a little bit.
How long?
Till 5 minutes, 15 minutes.
15 minutes. Okay.
Okay, so then I will explain a little thing, so you can start with the programming exercise, and we will do the exercise. So on the wiki there are sheets, but I forgot to print them, but for here I will write it on the board.
We can send this as many times as we want.
Yeah.
Yeah.
It's
Thanks.
yeah, but with my skills. I mean, the grader, I hope it's stable.
There's a gentleman agreement not to DDoS the grader.
Or to